chapters 3 and 4. Chapters 3 and 4 are sort of the high point of the class, or the low point, I guess, depending on how you look at it. But once you do those chapters, we'll start moving on in different directions. We'll still utilize some of what we've learned in chapter 3 and 4, but mathematically it won't be the same. It's going to be a lot different. Okay? I appreciate your understanding on Friday. I was out, and I know that maybe I might have missed a few of you, but I appreciate I was able to go out to this meeting and take care of some stuff. So I just appreciate that, and I understand that everything went okay with the exam, as far as I know. But if you have any issues, please come see me, come talk to me, okay? Chapter 5 is on energy. We'll look at work and energy in this chapter. And there are lots of different kinds of energy. But in this chapter, we're going to talk about the energy associated with motion. That's so-called kinetic energy. Or we're going to talk about that associated with the potential for motion. So we'll either talk about things that are moving or things that could move. So for example, if I throw this, it has kinetic energy, but if I hold it in a position where it has the potential for motion, then we would say that it has potential energy. And I can release this potential energy just by releasing the object. And so it has the potential for motion. And collectively, we'll call these mechanical energy. But there are lots of different other types of energy that we'll talk about later in the semester or even in the next semester. Those include thermal, nuclear, electrical. We'll deal with thermal later in the semester. Nuclear, we'll never see nuclear in this class, though it can be on the MCAT, so make sure that you read up on those chapters. I think y'all covered a little bit in Chemistry 106, if I'm not mistaken. And electrical energy. And next semester we'll deal a lot with electrical energy. So lots of different other types of energy. When we talk about work, we're going to talk about the physics definition of work. And work is done when a force is applied over some displacement. So you can have a force and you can have a displacement, but if you don't have both, then you don't have work. So for example, I can push on this desk all day long, and I'm not doing any work because I'm not moving it. And likewise, I can move in a direction at a constant speed, and there's no force causing that motion. So even though I have motion in a certain, even though I have a displacement, if there's no force causing that, then there's no work done. So you have to have both the force and displacement. And we'll sort of explore that idea and what it means as we move along. If our force and our displacement are parallel, then work is just equal to F times D. So for example, if I have this object right here, and I apply a force to it, moving it, the force in this direction, I move this object over a certain distance, delta x, or times d, then my work is just equal to the force times the distance. And then the unit for the work is the joule. And it has the basic SI units. We've done this before. Remember we did it for newtons. Remember when we did it for newtons, we said, we started with F equals MA, and then we said, well, M is kilogram meters per second squared. We're going to do a similar thing here. When we find the basic SI units for the joule, we know that work is equal to force times displacement, which is going to be kilogram meter per second squared, and then our displacement is also meters. So the basic SI units for the joule are going to be kilogram meters squared per second squared. Those are the basic SI units. I could ask you that on the test. I didn't on this previous one, but I sometimes do that. All right, so those are the basic SI units. As I told you before, when you capitalize a unit that's based on somebody's name, or rather when you abbreviate a unit based on somebody's name, you capitalize it. And so joules is named after a person, that's why it's capitalized. Okay, so if F and D are not parallel, then the component of F parallel to D is the only component of the force that does work. And so here I have a force off in this direction that's pulling this object in this direction. The displacement is in the x direction, but the force has both x and y components. The y component is along the y-axis here. The x component is here. This is Fx. The x component is the only component that's doing work in this case. Why is Fx the only component of the force that is doing work on this object? What about the object means that only Fx, not F at y, is only Fx doing work on this object? Think about this a second. Why is Fx the only force here, the only component of the force that's doing work on this object? Why is that? The displacement, right. The displacement is only in the x direction. So Fy is not doing any work. So Fy, no displacement in the y direction. So no work done by Fy. But the x component is doing work. And that work is equal to Fx times the displacement, which is in the x direction. So I'm going to put a little x subscript, which is going to be F cosine theta. That's just the x component of that force times d. So this gives us a more general expression for work, and we usually write it like this. Work is equal to Fd cosine theta. Where, in this case, Fx is the only force that does work, or the only component of the force that does work. Okay? You with me so far? Yeah? Alright. If there's no displacement in the direction of the force, there is no work done by the force. So for example, if I have this bucket of water, if I have this, and I'm exerting a force upward in the y direction, but then I move it around the room at a constant speed, and if I'm moving it at a constant speed, that means there's no net force acting on it in the x direction. If I'm doing that, what is the work that I'm doing on this bucket of water? It's really your question. What's the work that I'm doing? Am I doing work on it, or am I not doing work on the object? No work at all, because I'm applying a force in the y direction to hold it up, but it's not moving in the y direction. Instead, it's moving around in the x direction. And so sometimes you can have forces that are acting, but they're not doing work, like this. Dissipative forces such as friction also do work, but they generally do negative work, because the displacement and the force are in opposite directions. Let's imagine this. I have my expression is W equals Fd cosine theta. Let's say that I have a block. I'm applying a force to it in this direction. It is moving in this direction. Say it has a velocity v in this direction. And then I have a frictional force that's acting in the opposite direction. So if I wanted to find the work that's being done by capital F, I would consider the angle between F and the displacement. What is the angle between F and the displacement? F is in the positive x direction. D is in the positive x direction. So what's that angle? They're in the same direction. So that angle is 0. Right. So F and D, for F and D, theta equals 0 degrees. And then work is Fd cosine theta or cosine of 0 degrees, and the cosine of 0 degrees is equal to 1. On the other hand, if I'm looking at my frictional force, what is the angle between F and the displacement? The frictional force always opposes the direction of motion, and so the angle between F and D is going to be not 0, but how many degrees? 180 degrees. And the theta equals 180. And so work is equal to F times D times cosine of 180. And what is the cosine of 180? That's equal to negative 1. And so this work is going to be equal to negative FD. It's kind of useful to know your cosines, so let me just remind you over here. The cosine of 90 degrees equals 0. The cosine of 0 degrees equals 1. And the cosine of 180 degrees equals negative 1. Do you remember your unit circle? Right, this is 0 degrees, 90, 180, 270. All this is saying is, if you think about vectors, is that the x component is only present here, or the negative x component is present here, right? But there's none on the y-axis. All right, that'll come up when we have some quicker questions here in just a second. Okay, we have a bunch of questions here, 4 different questions. Each of these blocks is moving to the left. So for all these blocks, they have a displacement that's to the left. And some of them have forces to the left, some of them have forces to the right, and some of them have forces up or in various directions. But all the blocks are moving to the left. Maybe they have other forces that are acting on them or whatever. For number 1, which of these forces does no work at all? Looking at each of the labeled forces F, for which force does no work? Is it the force on block A, block B, block C, or block D? Which force does no work at all? All right, let's stop at 1 minute. Or I'll go to 103. 103. Okay, good. A is right. The force on block A does no work because F is in this direction, D is in this direction, and so the angle between those is equal to 90 degrees. My D is in this direction. Theta equals 90 degrees, and the cosine of 90 is equal to 0. Which force does negative work? We know it's not A, right? We've already said it's 0, so it's either B, C, or D. Which force does negative work? Now think about how do the force and the displacement have to be oriented towards one another in order to do negative work. And let's stop at 40 seconds. 40? Okay, good. C is right. It does negative work, C, because our displacement is in this direction, and this angle theta is 180 degrees. Cosine of 180 is negative 1. Or just think, the force and the displacement, they oppose one another, and so that work is going to be negative. Hey, how do astronomers have a party? They plan it. Okay, these next two actually have two answers, but just put what you think. Which force does positive work? Wow, I guess I just told you the answer. But which force does positive work? What do you think? B can do positive work because the displacement is in this direction and the force is in this direction. But also notice that this force can do positive work as well, or at least partially. One component of this force does positive work, and the other component, the y component, does what type of work? Positive, negative, or zero? The y component of this force. Zero, right? Because there's no displacement in the y direction. All right, so, everybody put A. Or no, not A, put B, rather, B. B or D is correct. But I'm going to mark A correct. Stopping at 55. B. B. Okay, for that one. Which force does the most work? Well, let's try it out. Which of these forces does the most work? All right, let's stop at 28. Okay, the most work is being done by B. D actually does a smaller amount of work than B for this reason, that I have a component in this direction of the force, Fx, and then I have a smaller component, Fy. This force is split between two components. So Fx is smaller than this force over here. And so this force will do the most work out of all of them. Actually, the magnitude of the work, if it's positive or negative, both of these do the same amount of work. But one's positive and one's negative. Okay, when you lift an object, do you do positive or negative work? A positive or B negative. When you lift an object, you take an object, you apply a force to it, do you do positive or negative work? All right, let's stop at 40 seconds. Okay, good. A is right. I do positive work because when I lift an object, I'm applying a force in this direction, and I have a displacement in this direction, so that does positive work because they're in the same direction. No joke for you, but just sort of a little personal anecdote. Maybe it's a little too personal. I'm going to tell you anyway. You know, what do some people, or guys especially, what do they call their bathrooms? It's a guy's name. John, they call it they go to the John. Hey, they're going to go to the John, right? But me, like, I prefer to call it Jim, like J-I-M, because it just sounds a lot better when you wake up in the morning to say, hey, I got to go where? Gotta go to the gym. Instead of saying, I got to go to the John. That's not really true. Like, I just made that up. That's a joke. Not a personal anecdote. Okay. Does the gravity do positive or negative work? What do you think? Yeah, it does a negative work because here my force weight is in that direction, and so this will do negative work because the angle between them is 180 degrees. Okie dokie, let's see. Let's try a little test question here. Just calculating the work here. Unlike when we were doing inclined planes where we had to sort of finagle the angles, with work and energy, the angle that we'll use will always be the angle that's given. There's really not any way to do it. All right, let's stop at 155. 155. Okay, good. Look at y'all, that's awesome. Yeah, you'll see some questions like this. Not all will be this easy, but you'll see some that'll be this easy for sure. So here it's really just sort of plugging in the right values that we have. Work is FD cosine theta. The force that I'm applying is 40 newtons. The distance is 25 meters, and then the angle is cosine of 60. And that's, what, 1,000, what was the answer? B? Yeah, so it's 1,000 times a half is 500 joules. All right, remember what we're doing here, if this is our cart, this is our force, it's applied at an angle of 60 degrees. Really, the F cosine theta determines the x component of that force, and then we're multiplying it times the displacement, which is 25 meters. Okay? Did y'all do well on that? Oh yeah, so this was just sort of in the news, and actually this isn't even funny. Like it's kind of tragic, but it had a good ending. That's why I'm telling you. There was this. It was in the Daily Comment. There was a kidnapping at school the other day. Did y'all hear about that? It's okay. He woke up. I'm sorry. I couldn't keep a straight face. Kidnapping. He woke up. Not a real kidnapping. It's just some kid napping. Okay, let's do a few clicker questions in the back, okay? I hope y'all recognize some of the questions from the test on Friday, from being from the concept test, or being from the OpenStat, the homework, or even some that were like old test questions. Those are good places for you to practice. All right, let's stop at 53. 53. Good. B is right. No, you have to have displacement in order to have work. So you can't have work on an object that remains at rest. All right, let's stop at 43. 43. Okay, good. B is right. Friction does negative work because friction always opposes the direction of motion. So that force and displacement are in opposite directions. Can friction ever do positive work? We're going to skip this one. The answer is yes. There's sort of some special cases. Like, for example, why don't you write down the answer? I'm just going to explain. Like, say if you have a truck, and then you have an object in the back, a block or whatever. And in this case, as the truck is moving forward in this direction, my speed and my displacement are in that direction, the frictional force is also in that direction. I think we might have had a problem on the test like this where the book slides off the chair. Right, what happens? There was no force acting upon it. There wasn't any friction acting upon it. Well, a similar thing here. If there was no friction, then the box would just slide off the back of the truck. Or think about it more importantly, it would stay where it was when the truck takes off. But in this case, it does have frictional force. And here, the frictional force is actually in the direction of motion. So that's sort of a special case. Reminds me of when I was a kid, we would ride on the back tailgate of the truck. Did you ever do that? With your feet hanging off the back of the truck? Surprised we didn't die. Get arrested for that now. Baseball game, the catcher stops a 90-mile-an-hour pitch. What can you say about the work done by the catcher on the ball? All right, let's stop at 35. 35. Okay, here the catcher has done negative work. You can think about the catcher catching the ball. He applies a force on the ball that's in that direction, right? But as he's applying a force in that direction, the ball is moving in this direction. And so you have a force and a displacement that are in opposite directions, and so he's doing negative work. This is kind of important because we're going to move next into the work energy theorem, which says that if you do work, then you change the energy of the object by that amount. So this catcher is doing negative work. That means that he's taken away energy from the ball, and the ball is moving and then it stops. So he's done negative work. He's taken energy away from the ball. So here he's done negative work. Let's try this. All right, let's stop at 38. 38. Hey, good. That's very good. Yeah, so we'll get into rotation and tension and forces like that later. But if you imagine that I'm standing here and I have a ball on a string and it's going around over my head, like I'm swinging it over my head like that, the force due to tension is in that direction. Right, that's my force. But my displacement is always tangent to the circle. So it's not pointing up. I mean, it's sort of in the direction of the circle. And so here, these are always going to be 90 degrees apart from one another, so it's going to do no work at all. We'll get into more of that in Chapter 7, so don't sweat that too much. We'll talk about centripetal forces in Chapter 7. Y'all might be confused by this one, because we haven't talked about adding work. I can have multiple works being done on a single object, and in this case, the hand is doing positive or negative work. What's it doing? It's doing positive work. What about the weight? What is the work being done by the weight? Positive or negative? Negative. And because it's moving up at a constant speed, that means that this force and this force are the same, and so this one's doing the same amount of positive work as this one's doing negative work. Well, when an object has multiple amounts of work being acted upon it, we can just add those together. So what's going to happen when I add these works together? It's going to be 0, right? So the answer is D. All right, I'm going to stop at 121. Answer is D. Look at y'all. Y'all amazing. All right, we'll come back to this. Just a few more minutes, then I'll hand your test back. But let's do a little bit of this kinetic energy and work energy theorem. So kinetic energy is the energy of a moving object. It's the energy of a moving object, whether it's an alpha particle or whatever the object is. It'll have kinetic energy. And we calculate this as 1/2 mv squared. There's a story about Emily de Châtelet. She was a 17th century scientist. No, 18th century scientist, I think. It was during the time of Voltaire. Was he 18th or 17th century Voltaire? Any history buffs? Yeah, anybody know? Well, I'm going to say 18th. We'll assume that's right. I'm pretty sure it's 18th. 18th century scientist. And she was interesting because she was a woman, and in the 18th century there weren't many women scientists, and obviously that's not true today, but back then that was true. But she did this experiment where she studied the proportionality between kinetic energy and the velocity. And now we know that the kinetic energy is proportional to the speed squared, or the velocity squared. But back then, people didn't really like squared numbers. They actually, when you took two numbers and you multiplied them by one another, they generally thought that was an abomination, that it was evil. And so in science, often people would avoid squared numbers, which, you know, when we think back on it, I mean, it's easy for us to think back on it, but we think back on it and say, well, that's kind of silly because they use squared numbers a lot, right? What do they use squared numbers for? They were farmers, right? They wanted to calculate their yield and their crops and all that. They had to figure out the area of their fields and how many seeds they needed and how many crops they were going to produce, so they used squared numbers a lot. Anyway, she did an experiment where she dropped a ball, and she dropped it into some clay. And she dropped it from a certain height so that when it hit the clay, she knew it would have a speed v. And it made an indentation. An indentation, we'll call it h. But then she dropped a ball from another height so that when it hit the clay, she knew that it would have twice the speed that it originally had. Those kinematics equations that we did, they had that back then. And here, do you think that she found it to be twice the depth? What do you think? Did it go down twice as deep? Or what? No, it went down how many times as deep? Not twice, but 4 times as deep. So she found that the indentation made in the clay was 4 times the height of the original. So this was 4h. And so that was a cool experiment that showed that the kinetic energy is proportional to v squared. And then you can do similar things with the masses of the balls, and you actually find that the kinetic energy is proportional to the mass times, is proportional to the mass, giving us this expression for kinetic energy, 1/2 mv squared. The half actually comes about through calculus, which is how we define that. It's the integral of the work, but we're not going to get into that here. Alrighty. We'll see some questions next time on the concept test that deal with this fact that the kinetic energy is proportional to v squared. I'm going to stop there. I'm going to hand back the rest